Okay, so if we start with Newton's two laws, that the sum of the forces is the mass times the acceleration, and that the gravitational force between two masses is given by this newfangled law of gravitation that he just published. The goal is to show, prove, or otherwise sort of claim Kepler's three laws can be derived from this. The first of Kepler's laws, that planetary orbits are ellipses. Newton was able to show with a whole bunch of calculus and differential equations and things that we're not going to go into. Just trust me that Newton was able to show in his paper that if these things are true, the only possible stable orbits, in other words, a shape that is periodic and returns to itself exactly like we observe planetary orbits to be, the only possible stable closed orbits are ellipses or circles. Newton was able to show that. I won't ask us to do it. It's a big pile of math. Let's just take it for granted. Yes. Okay. Well, if this is all we were going to do is check them off and say Newton was able to show it, then this would be kind of a boring segment. But the second and third of Kepler's laws, we can prove ourselves with this setup. The other piece I need to tell you about Newton's law of gravitation, this is a statement that talks about the magnitude of the force due to the gravitational attraction. The rest of his law, the rest of his proposal, is that the gravitational force between these two masses is directed along the line between them, along the separation between them, inward. So if r, the separation distance increased, then they're getting farther apart. So negative r is the other way. This is it's along the line between them, and it's directed inward. And with that, we can talk about this. So let's write Kepler's second law in math, that the rate at which we sweep through area should be constant. In equal amounts of time, equal areas are swept. Okay, if we can say this, if we can show this, then we're good. Now, okay, so first question is, what is the area of an elliptical sector? And let's let delta t be small, so that the distance, I'm going to use a capital R here, the distance between the planet and the sun doesn't change appreciably during this delta t. It's a small enough interval that the radius doesn't have a chance to change very much. Which means we're actually looking at a section of a circle. If the radius is the same all the time, then we're looking at a sector of a circle. That sector has some central angle theta, according to how fast we move from point 1 to point 2. And we know the formula for the area of a sector, or at least I think we do. Well, we know the formula for the area of an entire circle. So we know the formula we know the area is equal to pi r squared if theta is equal to 2 pi, right? If the central angle is the entire circle, then we know that the area is pi r squared. What if theta is only pi? Only half a circle? All right, so it should be 1/2 of an actual circle. All right, fine. So what if the area, the angle is only 90 degrees? Oh, I'm sorry, that's 45. Is only 90 degrees. Well, that's a quarter of a circle, so it's 1/4 pi r squared. So, okay, so we divide this by 2, we divide this by 2, we divide this by 2, we divide this by 2. When this is pi, this is half a pi. When this is 2 pi, this is pi. It looks to me like this is always half of this. Instead of pi over 2, we're talking about pi over 4. So here I'm going to propose 1/2 theta in radians r squared. Well, I'll use a capital R like I said I was going to. If theta is 2 pi, then we get back to the thing. Okay, cool, this works. All right, so we're talking about an area that is swept 1/2 by some small amount of angle r squared per some amount of small time. The question is that constant? Good so far? But angle swept per time, we know what that is. That's omega. So this is now, we're saying 1/2 omega r squared. Is that constant? For no particular reason, except that we can multiply both sides of the equation by anything we want, anytime we want. Well, I'm going to multiply it by, I'm going to multiply by m, the mass of the planet, mp. Like r squared, question mark, constant, multiplied by m on this side. Now, the mass of the planet isn't changing, so the right-hand side is still just constant. Yeah, it's a constant multiplied by m mass of the planet, but it's fine. And for that matter, let's multiply both sides of the equation by 2 so that we can get a cancellation there, and we'll just pile all the constants over on the right-hand side. mr squared is the mass moment of inertia of a single mass rotating around a point, right? The moment of inertia is add up all of the mass r squared, and there is only one mass in motion. It's just one planet. So we don't need the summation because there's only one thing, and the moment of inertia is just mr squared, which is this thing we just wrote. So this is I omega is maybe constant, and I'm just gonna, yeah, it's a big pile of constant. I omega is the angular momentum. So let me nutshell this before we go further. If we can show that the angular momentum L of a planet is constant, then we we can show that the rate of area per time is also constant, and that's Kepler's second law. Okay, fine. The angular momentum flavor of rotational Newton's second law. Just like regular, linear Newton's second law, the sum of the forces is the rate of change of the momentum. So the sum of the torques is the rate of change of the angular momentum. If we can show that this side is 0, then the right-hand side is 0, and since we know that some amount of time is going by, the numerator would have to be 0, which means delta L would be 0, which means L couldn't change because final minus initial has to be 0. So if I don't know why this helps, but if we can show that the net torque on the planet is 0, then this is equal to 0, and then this statement is true, because if delta L is 0, then L can't have changed. Okay. I gotta come back around to this side so I can finish the story. Erase that. What is the net torque on the planet? Well, there's only one force acting. It's gravitation. It's the gravitational attraction from the sun to the planet. So the net torque is the torque created by this gravitation thing. Make that a better G. There we go. Which is the lever cross the force. Okay, so that's the size of the action distance, which we're calling capital R, because this is a small enough section that the radius doesn't change. Magnitude of the distance, the magnitude of the force is, I guess we're going to use this thing that Newton proposed, Gm1 m2 over r squared times the sine of the angle between them. But what is the sine of the angle between the radius direction and the gravitation direction? From the planet out, the radius direction points this way, r, and the gravitation direction, according to Newton's new patented, trademarked law of gravitation, points inward, along the line between the planet and the sun, inward. So what's the angle between them? (180°), and the sine of 180 is 0. So we have leveraged Newton's law of gravitation to show that the torque on the object is 0. And again, the torque is just Newton's second law for rotation. So here we've got Newton's law of gravitation and Newton's law of motion. Put them together, we can show that the torque is 0, which means that the momentum can't have changed. Angular momentum can't have changed, which means the angular momentum has to be constant. So we can make this a yes check mark. And then we can walk that yes check mark all the way back to finally conclude, yes, the area swept is equal for equal time intervals, or the rate at which area is swept is constant. Nice. Cool deal. Okay. So far so good. Newton is batting 1,000 so far. So what about Kepler's third law? So the second one is that equals sector area in equal time. 3. Kepler's third law had to do with the proportionality between the semi-major axis and the period of rotation, or of orbit, I suppose. Okay. Ellipse geometry is tricky to work with. As soon as you start talking about ellipses, you end up in like transcendental function land and integrals that you can't calculate and all this kind of junk. So I'm just going to consider a simple case, and that is a ellipse with 0 eccentricity. In other words, a circle. Suppose we have the sun and we've got our planet, or it's the Earth and the moon or something like that, and we have our planet in a special case, a special ellipse, a circular ellipse in this case. But as soon as we say circular, we know that the sum of the forces on this planet needs to be the centripetal requirement. Got to be true. I mean, otherwise it's not a uniform circular motion. The only force doing, and this again is Newton's law of motion, F equals ma. The only force acting is gravity, so gravity must be doing the centripetal job. So I guess we'll put it here, Gm1 m sun, I suppose. Mass of the sun, mass of the planet over r squared equals m. Now this m is the mass that is in circular motion, and it's mp v squared over r. So we've got the mass of the planet on both sides. We've got a radius in the denominator on both sides. And wait, I thought we wanted to talk about the period. Well, if we're traveling in this circular orbit with speed v, that means we're going a circumference every period. So 2 pi r over t squared, because that's the velocity, distance over time squared. And now, if we solve, let's see. All right, let's do the square and get that out of there. So I'm gonna square. We got 4 pi squared r squared t squared. And if we cross multiply and leave t squared on the left-hand side, then r comes over here, 4 pi squared r cubed, divide by g, divide by the mass of the sun. This whole junk is constant, and then t squared is proportional, according to that constant, to the cube of the radius. And if we make a little bit of an extension to an ellipse, When we're talking about the radius, we're talking about the semi-major axis, and that's exactly Kepler's third law. The scientific community went nuts. This is crazy stuff, that with just these two things, you can theoretically sort of put in a theoretical context the empirical relations developed by Kepler. Really, really cool stuff. But Newton wasn't done. The next piece of Newton's synthesis, so I complain that we name everything after Newton, but this gravitation thing, this is the real deal. This is like, yes, this should be named after him. Newton's synthesis, we call it. He claimed that not only do his laws of motion and gravitation describe and predict the motion of the planets out there, our astronomical observations by telescope, that the celestial bodies, the heavens themselves, are described by these two equations. Newton went a step farther and said that this gravitation thing works just as well here on Earth. The mundane, the everyday, the terrestrial, the ordinary, right here on terra firma, it works. It describes the celestial motion, that out there, and it describes the motion that we're experiencing here, that we're dealing with as in our lives. And everyone lost their shit. There's no, that can't be true. Those are the heavens, right? That's beyond us. That's something extra human, right? We can't know that. That's beyond our understanding. We live here on this rock, and this is this. Yeah, okay, we can engage with this, but that's out there. That can't be described by the same physics. That's so. I mean, that's so ordinary, right? How can the planets and the motion around the sun is what gives us life, like how can that be described by something as ordinary as dropping an apple? And the scientific community went nuts, for good reason, because it's a crazy idea. It's why would you even think that the one description works in the other context? It's a really, really cool, really, really cool idea. So let's try to justify it. And in this story I'm telling, the convincing way to tell it is to, well, first, I need to figure out what the value is for capital G. I need to figure out what the value is for the universal gravitation constant. So that's the next segment.